The next video in our regression series is about hierarchical regression, which I cannot spell, as evidenced by the missing C value right here. So, other than cutting me some slack from a bad spelling, let's talk about what happens when I want to enter data in steps in regression. So the real research question you're going to ask when you do one of these is, after controlling for something, could be demographic variables, could be anything, what happens next? Does our second set of predictors, or do our second set of predictors account for any more variance? So this particular example is, after controlling for demographics, does the extraversion of the participant predict how well they take care of their car? So we have a data set with gender, where 0 is female, 1 is male. The age of the participant, the extraversion of them, where low numbers are introverted, high numbers are extroverted, with the assumption that extroversion, probably people who like to show off or be outside and be with more people, are going to take better care of their car. Or maybe it's that introverts just really want everything to be clean. Who knows? Okay, so we're going to find out. Our DV here is our car score on how well they take care of their car. So let's calculate power for this. So in G-power, we're going to use F-test, and I kind of have this open from last time. So F-test here, linear multiple regression, but we're going to pick fixed model R-squared increase. And we're going to do that because we're asking about the increase in R-squared when I add the second set of predictors. So generally when you do one of these hierarchical regressions, you're interested in maybe the last step. How much extra variance am I getting in that last step? Otherwise, it's very similar to simultaneous regression. So what I'm going to do is not from variances here, but direct and enter a partial R. In this particular example, I set a medium effect size. Calculate transfer to main. Alpha is still 0.05, power is still 0.8. Number of tested predictors. Number of tested predictors is the number of IVs or X variables in that last step. In this example, it's 1. Total number of predictors is how many overall do you have. So we're only going to put extraversion in the last step, so that's 1. And then the total number of predictors is 3. Hit calculate, or if you're on a Mac, hit enter. So I need 82 participants to find a medium effect size for extraversion. All right, let's move over to R and start working through our data screening. I'm assuming at this point that you've done a bunch of these data screenings, so let's talk about specific regression-related issues with data screening. So I'm going to load my data set here, and it's going to have 4 columns. So the gender of the participant, which I need to recode into a factored variable, and the age, extraversion, and their car score. So looking at the accuracy, I can tell I need to do something with sex here. Age, there's no negative numbers and no unusual numbers for car people. Extraversion, I guess, runs from 0 to 100 in this example, and car also runs from 0 to 100. So the only thing we really have to fix is that categorical variable. So I'm going to just relabel those as male and female. So to get our assumption checks, we're going to run our final model, no fake regression, because we're running real regression. And so our final model includes all of the predictors. And that's why it's got final here with exclamation points. Our first model is going to have just the demographic variables, but we want to screen everything. And it's okay that this is a categorical variable. In a minute it won't be, but right now it's okay. So we use the linear model function. We say the DV is predicted by all of our IVs, just add them together. Dataset equals our master dataset. We won't run a summary on this output. We're just using it as a segue into getting our assumptions checks. And so if you've been following along in order here, this will only be like the second time that you've done multiple outlier data screening points. So we'll walk through that a little slower. First, we're going to calculate Mahalanobis the same way we've been doing all semester. What you'll do is use the Mahalanobis function, fill in the name of your data set, but remember we're going to subtract out any categorical columns like sex here. Okay, so that's where my -1s are coming from. Now the Mahalanobis scores, I need some sort of cutoff, so I'm going to calculate my cutoff score, just like we've been doing, using q-chi-square, our big important rule where we want to look for people whose scores are less than 0.001, so they're really crazy before we eliminate them, based on the number of columns that were entered into the equation. Okay. In that particular example, this is 1626 with 3 degrees of freedom, because we had car, extraversion, and age. Here, we're going to calculate how many people are greater than the cutoff score. Well, before, what we had done is done how many people are less than the cutoff score, and we were interested in people who weren't less than the cutoff score, because that meant that they were an outlier. Now we're just going to calculate how many people are greater than the cutoff score. The advantage to that procedure is that we can save those values. So now you've seen here, I've done down here, Mahal greater than cutoff. Oops, Ahal, hee. And I've got a bunch of falses, so everyone's scores look okay. This as.numeric thing translates that into zeros and ones. So 0 here indicates that they're not an outlier. 1 indicates that they are an outlier. And that'll be handy when we're totaling those up in a minute. So we're just going to save those as bad Mahal. So where, remember, 1 is an outlier. If you're in my class or you just want to see, you can run in the table function to calculate how many people are outliers given this coding system. So 0 here, no outliers because there are no ones. So we don't have any Mahalanobis outliers. The next thing we're going to do is calculate leverage values. Remember, leverage is the influence one person has over the slope. So you're going to enter K as the number of predictors here. That's going to be 3, sex, age, and extraversion, predicting car, right? But there are only 3 predictors. Don't confuse this with the degrees of freedom for Mahalanobis. They're both 3, but that's only because sex got excluded. So to get our leverage values, we're going to use the hat values function and then calculate on the output. That output is from this final model that we ran up here. And so there are 3 predictors, 1, 2, 3. Mahalanobis had 3 degrees of freedom because it included car. So car, no sex, age, and extraversion. They don't always match. All right, so we run K equals 3. Calculate our hat values. So the only one you want to change is here. All of the rest of this should stay the same. We have to have some new cutoff score for this though. The formula for that is 2k plus 2 divided by n. Be sure you leave in the parentheses so that you use the right order of operations in R. And what this does is it just calculates how much the slope has to change before a participant is unduly influencing that slope. And the nice thing about this is that these numbers are going to be small and positive, which we'll be able to check if we're kind of doing it right. So small positive numbers here. So our cutoff score is 0.2. We're going to calculate how many people are above 0.2. And it looks like only one person score exceeds that criteria. Okay. Next up is Cook's. Cook's is a measure of influence on the slope and discrepancy, how far away people are from the rest of the data. To get those Cook's values, we're going to use Cook's.distance on our output from our final model. We're going to do this cutoff score formula, so 4 divided by degrees of freedom residual, which is n minus k minus 1. And that formula is in row of our data set, whatever data set we're interested in here. It might be no typos. In this particular example, it's master. And then we'll do minus k minus 1. Okay, so I'm here. So our cutoff score for Cook's is 0.11. It is small and positive and close to leverage. So they'll all be small and positive, like less than 1. Usually. If you get negative or large numbers, you've done something wrong. Let's see how many people are above that cutoff score. So we have 2 people who are outliers on Cook's distance only. Now I have 3 of these. What do I do with it? So I'm going to total up all 3 of those, and we're going to use a somewhat baseball rule. It's 2 strikes, you're out. And so we'll see how many people have 2 indicators or more. You might have 3. And in this particular data set, I have 38 participants who have no indicators. one participant who has one indicator and one participant who has two indicators. So remember the top row here is how many different outlier components you were a bad person on or that you were past the cutoff score on. And then down here is how many participants fall into that category. Because this is a frequency table. We're going to get rid of this one participant who is more than 2 by using this function here. So we're going to subset our master data set where our total outliers is less than 2. You'll see down here that the master data set has 40 and our no-out data set has 39. So we have one person who is an outlier on cooks and leverage. Because we are eliminating participants, we have to rerun our final model here. And that is just so that we can check the rest of our assumptions using that final model, but with no outliers. Because you don't want to screen your data set with outliers after going through all that trouble to exclude them. Now, the rest of these assumptions are set up in the same way that we've been doing all semester. So we're going to kind of run through those pretty quickly. But a quick note on additivity. On additivity, the rule is technically 0.9. You don't want your IVs to be too correlated. At 0.7, we're running the risk of suppression. So one thing you want to just make sure is when you look at this, is don't talk to me about the DV. So CAR here is our DV. And I'm not really interested in whether or not the IVs are correlated with CAR at this moment, because that's the point of the analysis, is to see how correlated they are with our DV. So we're really more interested in how correlated are our IVs. And you do have to exclude your categorical variables. So I've got age and extraversion here at 0.4. That's okay. And that's one thing this talks about here, is to make sure that you don't look at your DV. One other way that you can do that is run a summary on your output and do correlations equals true. Okay. Normally that would give me a correlation table at the end, but I either ran something or it won't do it because there's a categorical variable. Correlation singular, there we go. Correlation singular, no S here. Can't believe that didn't give me an error message. All right. Anyway, so then that pops up at the bottom here. So I could ignore the intercept. I could look at the correlation between the predictors here. And everything looks good. All right. The other thing we're going to do is set up our assumptions like we normally would. So we're going to use calculate our studentized and standardized residuals. And then our fitted scores. Remember, the fitted scores are our y-hat, so it's your predicted score. We're going to scale those so that we have easier way to interpret our pictures. So we're on a histogram of the normality. So this is a histogram of the residuals to look at normality. This is not random, so we should all get the same ugly picture here, and it's slightly bimodal. So it's problematic. It is centered between 0, kind of centered over 0 and between 2 and 2, but this double hump thing is problematic. So the data might be slightly bimodal, potentially due to our categorical variable. Looking at linearity here, that's pretty good. We're pretty close to the line. Homogeneity, 2 to 2, nice even spread. Couldn't have made a better graph if I had tried, right? So it runs from 2 to 2 and 2 to 2, fairly evenly. Homoscedasticity, this is just a bunch of dots. So those are looking good. So maybe some slight problems with normality. We have at least 40 people, so we should be fairly robust to the violations of normality. And this walks through and explains that with some funny commentary about how pretty some of these look. Now we're going to run things in steps. And so be sure that each subsequent step, so step 1 to step 2, includes the previous variables. You're adding variables to the equation, not switching them out. Because then you cannot compare models, because it's not fair to say that something is being controlled for and then take it out of the equation. So let's run model 1 here of just our demographic variables. You'll see that I've switched to calling this model because this is the real regression. So it does take about 80 lines of code, spacing and cute labels to screen the data, and then running the data is actually pretty quick. So we're going to predict our car variable with sex and age here, and look at a summary of that model. I'm going to come back over here. So first question, is the model significant? And given that we're doing this in steps, we're only going to interpret predictors in the step they're entered. So we're going to talk about age and gender here, but not later. So is that overall model significant? So you're going to get that from this last line here. So we've got 2 and 36 equals 2166. P-value is less than 0.001. Our R squared is nice and large, 0.55. So you can tell this is made up data. This is a very big effect size. I would not expect to find something that large normally. Now, looking at the individual predictors, I'm going to scroll back up. So I've got my gender and my age variable. So B here just represents the under the estimate column. For categorical predictor, remember from our dummy coding video that that's simply the difference in the DV between our two groups. So our car scores, it looks like guys are taking much better care of their cars than women. Our T value, so that 36 comes from the second degree of freedom here. 6.0 from this T value column, and here's P. And then the second one, age, for every 1 unit increase in age, we're getting 0.54 increases in car care, because as you get older, you realize maybe I want to take care of this thing so it'll last longer. And then our T value is 2.92, and this P value is 0.006. I don't know why it says 001. Okay. So my interpretation is that males have higher car scores than females. You can run T-apply to look at those means if you aren't sure. And as car scores, as age increases, we have higher car scores. So one thing we want to do is maybe figure out beta and look at which one of those is the better predictor, because they're certainly not in the same scale. So this is where quant sci is really useful. And we're going to do lm.beta of our original model, and it's pretty like grump, grump, grump about us, but we can use these two numbers here. So it looks like gender is a much better predictor than age. Now one problem we're going to have with running the partial correlations is that it will only use the variables in that step. That's the first point here. But the second point is no categoricals. So partials for this particular thing is not super useful because we have a categorical variable and we have to exclude it even though it is being included in the equation. So I can run that using the PP core library. I'm going to calculate my partials, but I have to I'm excluding 2 and 4. Remember, you can type in names to figure out which ones to exclude. So, what? Oh, no, I'm not excluding. I'm sorry. I'm including 2 and 4. So, age and car. And then I'm squaring that. But that's not as helpful, maybe, as another formula that you can use, which is t squared divided by t squared plus df residual. So I could calculate these better by using the actual t values from the model. PP core is just a little easier if you have a lot of these. So I could take my t value from the equation and actually get this as well for gender. Oops. So that model squared, so the little caret thing is above the 6 on a QWERTY keyboard, American QWERTY keyboard. Plus degrees of freedom residual here, which is 36. That tells me it's 0.5, which is a very big number. I want to do that same thing now for another one. It's just 0.19. These add up to more than r squared. You did not do anything wrong. Remember that PR squared values have different denominators. And so they could add up to r squared, but they're not supposed to. And they actually can add up to more than r squared. And that's okay. Now these match our beta values in that the gender variable is accounting for a lot more variance, unaccounted for variance, than our age variable, because it's like twice the size as for beta and about twice the size for variance. So these tend to agree. But that's just another little formula, especially if you're working with categorical predictors. Okay. All of that is step 1. Now let's get into step 2. Step 2 is where we're going to add, so we could add here that variable, and you'll notice that this number is different. That's because now if you do it this way and you don't include gender, this is actually just the squared correlation between age and car, and it doesn't control for gender. And so if we control for gender, we're actually going to get a different number. So for part 2, now we're going to add in the next variable. So we've got sex plus age plus extraversion. Don't exclude these. That's the biggest mistake that people make, at least in my homework, is that we're adding variables as we go. Okay. So this is step 2. And we want to look at the same questions, except now, is the overall model significant? Well, yeah, it is. So 3 and 35, p-value, here's r squared. That just tells me if r squared is greater than 0. And that includes all of the variables. I want to know if the change between model 1 and model 2 is significant. And so how much does extraversion help us? So does the addition of that step help us out? And what we can do is we can actually use the ANOVA function, which does not run ANOVA. It compares models. So let's look at that over here. So ANOVA model 1, comma model 2, always put the simpler model first. And it'll show you what you've done. So this is step 1, and there's step 2. So you can see we added extraversion. It's going to compare step 1 to step 2 and give you a bunch of numbers here. So what you want to do is look at the DF here, and then the DF here. So 1 and 35 is, here's F, 5.96, here's P. So yes, the change in F, so that's a little delta symbol, is 5.96, P is 0.02. The change in R squared is 0.06. That's not here. I just subtracted model 1 minus model 2. So I scrolled up here and I said 0.61 minus, scroll, 0.55. So that's how I got the difference in R squared. So the addition of extraversion is adding 6% of the variance, which is almost a medium effect size. Is extraversion overall a significant predictor? Yes. So I'll come up here, little 0.34, here's T here, here's 0.02. Okay. And we can calculate PR squared by using our P-core thing again, but this time now including extraversion. Right? And that would still exclude sex, so we could also do this formula way. I'm going to put in quant sci. It's going to be unhappy with me again, but I can tell the extraversion is a stronger predictor than age, but maybe not stronger than sex. Now these will change from above because now we have an extra variable in the equation. But if you're wanting to compare that one to your previous steps, you could. All right. So we've already talked about PP core. We're just going to run a graph now. So what's going to happen is the x-axis on the graph, we've got 3 variables, and we can't really layer them together and make a crazy 3D plot. So instead, we're going to put on the bottom our fitted scores. So these are our y-hat values. And then we're going to plot those against our actual y values and hope that our y values and our y-hat values line up together. So I'm going to run ggplot and run some cleanup code here. I must get those fitted scores. That's the same way we do this for data screening, except it's on the final model and they're not standardized. We're going to create a scatter plot of our fitted scores on X and our DV on Y. On this scatter plot, we're going to clean it up, add some dots, add a line, a straight line, color it black. On the x-axis, I put in all 3 variables because it is actually the combination of all 3 here. And y is our car care score. If we've done this really well, the line will be fairly straight and the dots will be close to the line. And so essentially what's happening is I predicted your score to be 19, and it looks like your actual score is 15. So I'm a little under what your score should be. Here I predicted your score to be like 22-ish, and you actually got 24, so I'm a little over your score. So dots above the line are, we estimated too high. Dots below the line, we estimated too low. Dots on the line mean we got you perfectly right. So we want most of these dots to be fairly close together. And then we get a confidence band of how close y hat and y actually are. So we want this to be skinny. Okay. How would I write this up? Well, you would want to include a little bit of information about data screening, especially if you eliminate any outliers or have any issues with your data screening. So I probably should have written that normality was a little suspect here. Then talk about each step sequentially. So talk about the first step, overall model is significant, gender, age. Then talk about the second step, and here I've included the change in F and R squared, and then the information about what was entered in that step. So you talk about each step one at a time. Be sure to include the F values and the predictor values. You can use B or beta, just be consistent. And all that together is a hierarchical multiple linear regression, starting with data screening and working through write-up.